Hey guys, welcome back. Today we are going to learn about some characteristics of vectors. So an introduction to vectors first, a couple different types of quantities. One is a scalar quantity. In a scalar quantity, you're talking about magnitude only. Which means it is non-directional. Okay, so some examples. Volume is non-directional, it's only magnitude. Mass, money, distance, things like that are only a magnitude and no direction. A vector is referring to magnitude and direction. Okay, some examples would be things like force, velocity, displacement, and things like that. So there's some examples of vector quantities. Vector quantities are very important in physics, engineering, navigation, and many other areas. So vectors, they are direction and they are magnitude. The direction on a vector is represented by an arrow. An arrow like this. The starting point, that's the initial point, that is called the tail. So this right here is the tail. The ending point, or the terminal point, is called the head. So that is the head. Something to keep in mind is that usually when you see something like this with an arrow, it means it's going forever in that direction. But on a vector, that head is a terminal point, so it does not continue forever. The arrow only shows the direction. It does not show that it goes forever. So that's direction. Magnitude is the length of the arrow. And since it is a length, the magnitude is always a positive number. Okay, and a vector can be symbolized by an arrow above a letter, like vector A. Equal and opposite vectors. Two vectors are equal if they have the same magnitude and direction. So here's two vectors, exactly the same direction, and they both have a magnitude of 5. They can start anywhere. They don't have to be right on top of each other. They don't have to have the same end point. They just have to go the same direction and have the same magnitude. A vector in standard position starts at the origin. Opposite vectors have the same magnitude. This one has a magnitude of 5, just like these other ones do. And note that all three of these happen to go the same direction. This one has that same magnitude, but its direction is opposite. So an opposite vector has the same magnitude, but it goes exactly the opposite direction. We can add vectors graphically. So we've got two vectors here on a graph, and we can add those together. It is not like arithmetic. We're not adding a couple numbers. Okay, so we're not going to add their magnitudes mathematically. It adds according to what's called the parallelogram law. And according to the parallelogram law, we can string vectors together, head to tail. And we'll put in a description for the result after we actually do one. So we've got vector v and vector u, and we want to add them graphically. I'm going to leave one of them with its tail right there at the origin, and I'm going to move the other. Typically, it's easier to leave the longer one and move the shorter one, but it really does not matter. So this shorter one, vector v, goes 1 to the right and up 4. So I'm going to take this vector and slide it down to the head of vector u, and from the head of vector u, I'm going to go right 1 and up 4. Okay, so there is an image of vector v. Okay, so I have moved the only one that I'm going to move. I left one and I moved the other. So now I'm ready for a result. The result is a new vector. And it goes from the initial tail to the final head. So the initial tail is where it all started. The final head is where I ended up when I moved this one down to here. So here is the resulting vector. So this is vector u plus vector v. In this next one, I have 3 vectors that I want to add together. And it does not matter the order that I add them. So I'll leave w right where it is. So w is going to stay here. And I'm going to take u and slide it down to here. And u goes over 2 and up 3. So from here, I'm going to go right 2 and up 3. So I have moved vector u to right there. Then I'm going to take vector v and slide its tail to this head. Vector v goes left 6, or goes left 7 and up 7. So from here, I'm going to go left 7 and up 7. So there is vector v moved over to here. I don't have any left to move. I always leave one right where it is and move the others. So from the initial tail to that final head is my resultant vector. Okay, so we are going to sketch on this graph vector A, which is 3 times vector u. So vector u goes right 3 and up 2. That's once. I'm going to go right 3 and up 2 a second time, and then a third time. So I'm just going to tack that right onto the end of vector u, and there is vector A, which is 3 times vector u. Okay, so it starts here, and it goes all the way to here. Next is vector B, the opposite of vector W. Vector W goes right 6 and down 4. The opposite of that would be left 6 and up 4. So there is the opposite of vector W, that's vector B. C is vector u plus vector w, so I need to string those 2 vectors together. I'm going to leave w right where it is, and I'm going to take u and slide it down here. So vector u is right 3 and up 2, so from down here I'm going to go right 3 and up 2. And from the initial tail to the final head is vector u plus vector w, and that's called vector c. And last is vector u minus vector w, which is the same as vector u plus the opposite of vector w. So I'm going to add the opposite of vector w, which is b, to vector u. So again, u is right 3 and up 2, so from the end of the opposite of vector w, right 3, up 2, and there is vector d, u minus w. Vector A is 2 times vector u, so vector u, right 3, up 2, right 3 again, and up 2. And from this initial tail all the way to here is vector A, 2 times as long as vector u. Negative half of vector w. So vector w is right 6 and down 4. I want to go opposite, which would be left 6 and up 4, but I only want to do half of that opposite, which is left 3 and up 2. So that is half of the opposite of vector w. That's vector b. Vector c is 2 times vector u plus vector w. So I've got vector w here. 2 times vector u is right 6 and up 4. So from the end of w, I need to go right 6 and up 4. So that ends right there. So from the initial tail to the final head is vector c, which is 2 times u plus w. And then d is 2 times u minus half of w, which is 2 times vector u plus the opposite of half of w. So here's 2 times vector u. This one is half of the opposite of vector w, so I need to string these two vectors together. This vector is left 3 and up 2, so from the end of this vector, left 3, up 2. From the initial tail to the final head is vector d. Magnitude and direction form. So we're talking now about different ways to describe vectors. So one form of a vector is called magnitude and direction form, where you might be given something like this. Magnitude is 120, the direction is 23 degrees. So there is a magnitude and direction form. That might mean something like an airplane is flying 120 knots at a direction of 23 degrees north of east. You might also see a vector in component form. So here's an origin right here, 0, 0. Here's a vector, and it's got an x component, how far it goes to the right, and a y component, how far it goes up. So the vector's x component is the horizontal component. The vector's y component is its vertical component. Okay, so to get component form, the x and the y, we're going to subtract, so this is kind of like doing distance formula. Whatever this set of coordinates is, whatever this set of coordinates is. Let's say it's, well actually let's just use this. Let's pretend that's not the origin. So that is now going to be 4, 1. So if its initial point, the tail, is 4, 1, and the head is at 9, 3, we can find the component form by doing the head minus the tail, so the x from the head minus the x from the tail. So that would be 9 minus 4. And then the y from the head minus the y from the tail. 3 minus 1. So that would be 5, 2. So this is component form for that vector. We always must subtract head minus tail. Other forms of a vector, you might see something like this. Say 5, and then a little I, that caret over the top, plus 2j with the caret over the top. That I would represent horizontal, and the j would be the vertical component. Or you might see this. It's written as a matrix. There's your horizontal and your vertical component. And last thing we're going to talk about is the magnitude, which just means the length of a vector. It can also be symbolized like this. Or it could be double wall. Okay, all of those things mean the same thing. Magnitude, length, these mean the same thing. And that is found by doing the square root of the vector's x component squared plus the vector's y component squared. In this case, we had x and y components as 5 and 2. So 5 squared plus 2 squared under a radical. This right here is the distance formula. So you might be thinking the distance formula has subtraction in it, doesn't it? Well, that 5 came from subtraction. 9 minus 4 squared. And the 2 was 3 minus 1 squared. So this is the distance formula. When you're doing magnitude, length, that's distance. The only difference between this and the distance formula is that the subtraction here was already done right here. So it is the distance formula with the subtraction already done. So that's 25 plus 4. So the magnitude is the square root of 29. Okay, or it could be written like this. The magnitude of the vector is the square root of 29.